So now we're going to look at integrals which are quotients of polynomials of sine and cos, where integrated over one period. So this is rather a neat approach. It's completely different from the other contours. We basically make a change of variables and put z equals e to the I theta. So if we do that just from the formulae, well, we know that cos theta we can write as half e to the I theta plus e to the minus I theta. So that gives us cos theta equals half of z plus 1 over z, which we can write in this way, and similarly we can write sine theta like this. And if we differentiate, then we get dz equals I times e to the I theta d theta, which means that d theta is dz divided by I times e to the I theta, but of course e to the I theta is z. Okay, so that's enough for us to change variables. So the other thing to notice is that if the integral is period pi, 2 pi, it makes no difference where we start the limit. So if we've got phi to phi plus 2 pi as the limit, we can always change that to, we can put phi, we can change phi to anything. So phi could be minus pi or minus pi by 2, it doesn't really matter. We can change the limits to anything we like. So yeah, so just bear in mind. So yes, the 0 to 2 pi is just for convenience. This might be minus pi and plus pi is quite common. But we change it to 0 to 2 pi. Now, the whole idea of this approach is that as theta varies from 0 to 2 pi, what happens to z? Well, z just goes around the unit circle. Okay, so this is as theta varies from 0 to 2 pi, this is just telling you that z goes round a circle of radius 1 centered at the origin. So the original integral has now been transformed to a contour integral. We haven't actually had to think about the contour integral, it's just automatic when we change this variable. So the contour integral, or the contour, just looks like this, anti-clockwise integral on a circle, around a circle. So again, this is something you shouldn't really try to remember. You should derive these each time, or write them down each time. But basically, we've converted the integral we wanted, this one, into this form. And then, again, this is a formula you shouldn't try to remember. You should basically effectively derive it each time, which is not difficult. But I'm just summarizing what you actually find in the end. So finally, the integral itself is just 2 pi I times the sum of the residues of this, where the residues, of course, are of the poles which are inside the unit circle. That's what we're saying here. The modulus of the values of where the singularities are has to be less than 1. Now, the most difficult thing about this type of integral is nothing to do with the integration, of course, nothing to do with the change of variable. That's all straightforward. The difficult thing is knowing where the singularities are. Because unlike other cases where, I mean, for example, with the semicircular ones, it's basically everything above the real axis is a singularity. With the rectangular contour, it's generally fairly obvious where the singularities are, because we need to know where they are first before we choose the height of the rectangle. In this case, we always choose the same contour. We have to find where the singularities are and which ones are inside the contour. So I'm just mentioning this trick here. When determining which of the poles are inside the unit circle, just remember that if Z1 and Z2 are zeros of this polynomial here, then Z1 times Z2 is equal to B. So that means that, for example, if B is 1, we know that, and one of these is obviously less than 1, and that means the other one is going to be larger than 1, for example. Well, how do we know this? Well, where does this come from? Well, all you have to do is expand this. Then you get, and then compare with this. So if you expand this, you obviously get Z squared minus Z1 plus Z2 times Z plus Z1 times Z2. So the Z1 times Z2 is equal to B. This is a very useful thing to remember. Simple result, but useful. Okay, let's see how this actually works with a proper example. So we're going to integrate this. We're choosing A to be larger than 1, so this thing on the bottom is never 0. Okay, so we make the change of variable, which is straightforward to do, and I'm going to write the roots of this polynomial in Z as Z plus and Z minus for convenience. Obviously we can solve this using the quadratic formula. Which gives us Z plus or minus is equal to this. So obviously you've got simple poles at Z plus and Z minus. We need to know where those poles are. Are they inside the unit circle or outside? Okay, so we look at this. We remember that A is larger than 1. So if we look at the minus one, first of all, minus root the Z minus, then we see we've got minus 1, and we've got minus something minus 1. So obviously that's going to be outside the unit circle. So this is our Z minus. But now we need to show that Z plus is inside. You can probably argue that it has to be inside, because if it wasn't inside, this integral would be 0. So you could say something like that. We know this integral can't possibly be 0 because it's always the same sign. It's got to be a positive number. So you could use that to argue that Z plus is inside. Otherwise, we can use this idea here, that this is minus 1. That means the product of the roots Z plus times Z minus must equal minus 1. Since one of them is less than minus 1, Z plus must be more than minus 1, greater in magnitude than minus 1. Okay, and always draw the contour and your poles. It should be fairly obvious from this that, well, okay, I mean, also just looking at this, in this particular case, it's fairly obvious that it's got to be more than minus 1, but still negative, because you've got minus 1 here, you've got something here which is going to be less than 1. So you've got plus something less than 1 minus something which is equal to 1. So that's where Z plus is. Okay, so in this particular case, finding the residue, you do have to be careful to make life easy for yourself finding the residue. So I'm saying using the simple pole method 219, which one is that? This is one particular case where, yes, this is one particular case where actually the P over Q dash method is maybe not the best one to use. So I'm suggesting you actually use this one. So obviously we can write this as 1 over z minus z, z minus z plus, and the r is z minus z minus. So this is one particular case where 219 is actually the simpler one to use. So we just end up with the residue, where's it gone, as so the 2 comes from here, 2 over, so we're looking for the residue at z, z plus, so we get rid of this and then just substitute in z plus to here, and we get 2 over z plus minus z plus minus z minus. And okay, from this, then it's easy to find that, and use the residue theorem, multiplied by 2 pi I, and we end up with this as our final answer. Just some extra little tips, just to remind you that if you've got an integrand which is even, then obviously you can do an integral like this. So 0 to 2 pi, I mean 0 to pi, it's not a full period, but we can turn it into an integral over a full period if this is a even integral. And also importantly, remember that if the integrand is odd, the integral will be 0, because if this is odd and it's over a period, then you can always shift your range of integration to minus pi to pi, and if you're integrating an odd function over symmetric limits about the origin, then you'll always get 0. So just remember that. Okay, you can now do the next question.